So there's an interesting transition that occurs when we heat a liquid in a sealed container. So here the pressure is going to build up. As the temperature rises, the liquid evaporates, more gas is formed, and the pressure increases. If we continue heating, the gas becomes more dense. The liquid becomes less dense, because that's what happens to most liquids as they're heated. And at some point, the gas and the liquid states merge into one state. And that's called a supercritical fluid. So we have an illustration here. It's a little difficult to get good pictures of this because it occurs in a highly pressurized container, and so you can't just do it in a piece of glassware. So here's a little window into this container. Here we see the liquid and the gas. There are definitely two states. As we increase the temperature, the division between these two states begins to become a little bit blurred, and at a temperature above what's called the critical point, there is only one state. It's a supercritical fluid. It's not a gas, and it's not a liquid. It's weird. It's a weird state, right? Supercritical fluid. So the critical temperature is the temperature above which a supercritical fluid will form. Above that temperature, a liquid cannot exist. You can't have the liquid. The pressure that occurs at that transition is called the supercritical pressure. So let's think about that for a minute, because it may seem strange. Well, why can't you have a liquid at a certain temperature? Well, what if you try to heat water to 200 degrees Celsius? You can't have liquid water at 200 degrees Celsius at normal atmospheric pressure because it boils before it gets to that temperature. Under higher pressure, you can make the boiling point higher, but we can see that there will be a point at which it's just not going to work anymore. And that's the critical point. So supercritical fluids are very useful solvents. Probably the best known use of them, supercritical CO2 is used to decaffeinate coffee. So caffeine is soluble in some substances. It's soluble in water. It's also soluble in CO2. By using supercritical CO2, we can get the caffeine to dissolve. Caffeine won't dissolve in a gas, but it will dissolve in a liquid, and the supercritical fluid is between a liquid and a gas. So you can use the supercritical fluid to dissolve the caffeine, remove the caffeine, and then when you release the supercritical fluid, what's left on the coffee? Nothing. Because the CO2 is a gas and it floats away. And so we're not left with any residues by using any other chemical solvents. We can't use water to decaffeinate coffee because that's going to also take away some of the flavors of the coffee. So supercritical CO2 is used to decaffeinate coffee. Anybody have any questions?